Hello. Welcome back. Today is 31st December 2025. Oh, what is this, bro? Why is there so much shit in my glasses? Okay, it's 31st December 2025, and we are at day 16. Uh, we were doing probability distribution yesterday. We completed that sort of, and then today we are doing central limit theorem. And what are the other things we are doing with? Let me see. Where is it? For 10 minutes I kept the stream. So okay, skewness, central limit theorem. Yeah, I was right. Central limit theorem and hypothesis testing. Okay, so we are doing that today. It's around 4 articles, or wait, yeah, 4 articles, 8 MCQs. Easy, it will be completed. I know about that. And Happy New Year. Tomorrow is New Year, and also what I wanted to talk about. Okay, I will not be doing stream on 10 and 11. Okay, Jan 10 and Jan 11, January 10 and 11. There is event, so I'll be going and I'll not be present. So Jan 11 and 10 will be my break day. Others are same. Okay, so the days won't be counted. The days will be if day 25 in 9th Jan, then I'll come day Monday 26. Monday will be 26. Okay, I'll take 2 days off for me, and that is because I can't shit here 24/7. What the hell happened? Oh shit. Okay, I can take breaks. Okay, but uh, I have to confirm on this stream before 7 days. I guess 7 days. That would be enough. If it's urgent, then I'll do it at night. Yeah, I can do it at night, right? 26. Yeah, I guess I'll be able to do those 2 days, but I'll do that at night. I'll do 2 hours night, right? It would be fun. Okay, then let's get back to our session, and we'll do that Geeks for Geeks one. We'll learn that too, and some typing. Further, if there is something else, we'll do that too. Okay.
Why'd you let me fall, girl? Why'd you let me down? Why'd you give me up before the end of the world? Did you hear me screaming? Stop screaming loud. Did you hear my cries before it all came crashing down? Why'd you let me fall? I know I waited too long, left you alone. Your love, it closing in on me. It's all in my head and I know that I don't belong. I don't think I'll escape this hell. This hell. I don't really think you hear me. Demons all are running near me. Pouring up, I'm numbing feelings. Folding every hand they dealing. Now I feel I'm inching towards the other side. Why'd you let me fall, girl? Why'd you let me down? Why'd you give me up before the end of the world? Did you hear me screaming? 'Cause I was screaming love. Did you hear the cries before it all came crashing down? Why'd you let me take your heart and break it to a million pieces? Oh, I can't forgive you 'cause I'm too far gone, and now I'm chasing after myself. Caught between the form of everything that life it throws alone. It always seems to be so fucking wrong. There's no way I could leave this hell. I don't really think you hear me. Demons all are running near me. Pouring up, I'm numbing feelings. Folding every hand they dealing. Now I feel I'm inching towards the other side. Why'd you let me fall, girl? Why'd you let me down? Why'd you give me up before the end of the world? Did you hear me screaming? 'Cause I was screaming love. Did you hear the cries before it all came crashing down? Between us, I know if it's short. There's a gate I see. There's a way for me. Now this one sits here and whispers things to me. Now I got the devil
What?
inside. This one made a pig of me.
What?
This world is primal. My grinding joy.
DD. Wow, what is that? What?
हुए अखियां दे मेरे लब दे नैना तेरे सारी सारी रात आवे नींद ना मैनू दिल दी बारी मेरी तक तक रावा तेरी पुछदी है बैरी आवे क्यों ना आया तू शाम सुबह तेरी फिक्र है शाम सहर तेरा जिक्र है रहते हैं हम बिखरे बिखरे धड़कनों से ना तेरा लिख रहे शब से तेरा फिक्र है शाम सहर तेरा जिक्र है रहते हैं हम बिखरे बिखरे धड़कनों से ना तेरा लिख रहे पावा तेनू याद अंजावे क्यों सुने ना माया तू इन्ना क्यों रुलावे होई ना किसे दी कदी बस तेरी होई रही मैं भी यही सोचदी आ क्यों मिलाना बुए अखियां दे मेरे लब दे नैना तेरे सारी सारी रात आवे नींद ना मैनू दिल दी बारी मेरी तक तक रावा तेरी पुछदी है बैरी आवे क्यों ना आया तू शाम सुबह तेरी फिक्र है शाम सहर तेरा जिक्र है रहते हैं हम बिखरे बिखरे धड़कनों से ना तेरा लिख रहे शब से तेरी फिक्र है शाम सहर तेरा
What
जिक्र
the
है
hell?
रहते हैं हम
Let's stop that. And read. not to host this, but let's look at the weight of the articles. CLT, hypothesis testing.
Hello everyone and welcome back to Geeks for Geeks. In today's video, I am going to explain you hypothesis testing in detail. So without wasting any more time, let's get started.
Hypothesis testing and skewness.
Hello everyone and welcome back to Geeks for Geeks. In today's video, I am going to explain you hypothesis testing in detail. So let us move on to the implementation part where I will show you the code. So first of all, let me tell you what is hypothesis testing. Hypothesis testing is a statistical method that is used to make a
We can do this first and then you read, okay? So, first, let's look at skewness. Is not enough. Skewness, right? Skewness is a key statistical measure that shows how data is spread out in a dataset. It tells us if the data points are skewed to left, negative skew, or to right, positive skew, in a relation to the mean. It is important because it helps us to understand the shape of the data distribution, which is important for accurate data analysis and helps in identifying outliers and finding the best statistical methods to use for analysis. In this article, we will see skewness, different types of skewness, and its core concept. Okay, mean, median, mode, no skewness, so bell-shaped curve. Bell-shaped curve, it's a positive skew. Mean is less than median, and mode is greater than median, so it's a positive skew. And mean is less than median, and mode median is less than mode, so it's a negative skew. Okay, am I right? Right skew, like look, in positive skew, mean is greater. Sorry. Mean is greater than median and greater than mode, and median is greater than mode. Right? Then it's positive skew. Sorry about that. It was opposite. Mode is greater than median, and median is greater than mean. Right? Got it. Skewness describes the direction and degree of asymmetry in a dataset distribution. Various types are as follows. Positive skewness, right skew. In a positively skewed distribution, the right tail is longer than the left tail, which means most data points are on the left with a fewer larger values pulling the distribution to the right. Okay, data points are on the left to relationship. Mean is greater than median and greater than mode. Income distribution, exam score and stock market returns. Income distributions, exam scores and stock market returns. Negative skew, left skew. In a negatively skewed distribution, the left tail is longer, which means most data points are on the right with a few smaller values pulling the distribution to the left. Um, if I look at this way, in left, right, small. Uh, the left tail is longer, which means the left tail is longer. Okay, mean is less than median and less than mode. Then it's negatively skewed. The test scores on easy exams is at retirement and mm, G gestational. Gestational is at birth. Ooh.
Gestational.
Gestational, 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 gestational. No. What the? The speed was not good. No, this was better than this runs. Okay. 10 test scores on easy exams is requirement and gestational is at birth, right? Okay. There is skewness, symmetrical distribution. Is greater. Their skewness shows a perfect symmetrical distribution where the mean, median, and mode are equal. In a symmetrical distribution, the data points are evenly distributed around the center point relationship. Mean is equals to median is equals to mode. A perfectly balanced data set with equal frequencies of all values. Test of skewness. There are several ways to find the skewness of a data set which can help to find whether the data is positively skewed, negatively skewed, or roughly symmetric. Below are some common methods used to measure skewness. Visual inspection. This is the simplest and quickest method for assessing skewness by creating a histogram or a density plot of the given data. If the plot has a long tail on the right, the data is positively skewed the right skewed. The data has long tail on left, negatively skewed left skewed. If point is roughly symmetric, the data has no skewness, zero skewness coefficient, Pearson's first coefficient of skewness. In this is a numerical method of skewness based on the relationship between the mean and mode. It helps us to find if the data is skewed when the mean and mod are not equal. This is numeric measure of skewness based on the relationship between mean and mode. It helps us find if the data is skewed when the mean and mode are not equal. The mean and mode are not equal. Positive skewed if the mean is greater than the mode, the skewness is positive. Mean is smaller than the mode, the skewness is negative. If the mean is equal to the mode, the skewness is zero, which indicates symmetric distribution. Skewness based on quartiles. Skewness based on quartiles. This method checks the distances between the quartiles to find skewness. If the quartiles are not equidistant, it suggests skewness. The third quartile Q3 minus the median ME should ideally be equal to the median ME minus the first quartile Q1 in a symmetric distribution. If this condition is not met, it shows either a positive or negative skew, which depends on which side is longer. Okay, skewness based on quartiles. This method checks the distance between quartiles to find skewness. If the quartile distance, it suggests skewness. Third quartile minus the median should ideally be equal to the median minus the first quartile. Median is Q2 in a symmetric distribution. Condition is not met, it shows either a positive or negative skew, which depends on either mean minus mode. Skewness coefficient, Pearson's first coefficient of skewness. Positive skew if mean is greater than mode, and mean is smaller than mode. Then negative skew, that we already know. Measurement of skewness. Skewness is measured using different techniques to quantify the degree of asymmetricity in a dataset distribution. Below are three common methods to measure skewness. Carl Pearson's measure use the mean, median, and standard deviation of the given data to measure the asymmetry of the distribution. It provides a dimensionless number that helps to quantify how skewed the data is. Formula with respect to mean and median, SK3 Measurement of skewness. Skewness is measured using different techniques to quantify the degree of asymmetry in a dataset distribution. Below are three common methods to measure skewness. Carl Pearson's measure. Carl Pearson's measure uses the mean, median, and standard deviation of the given data to measure the symmetricity of the distribution. It provides a dimensionless number that helps to quantify how skewed the data is. Formula with respect to mean and median, as k is equals to 3 mean minus median by standard deviation with respect to mean and mode. Mean minus mode by standard deviation. Sk is Carl Pearson's skewness coefficient, mean of the data set, median of the data set, standard deviation of the data set, and interpretation. Skewness is equals to 0. Distribution is symmetric, means the mean, median, and mode are equal. Yes. Uh, it's always like this, man. Type out.
जानते हैं तुम सा न कोई इश्क की है कैसी कहानी पर दो पल में दिल मेरे में है सब खो दिया क्या सोचा था क्या होना फिर मुँह क्यों
My
मोड़िया
mind is not
दिल
right
लगाने
place.
से मिला है दर्द कैसा क्या बताए उलझनों में दिन है मेरे काटे कैसे क्या बताए जान के भी दिल ये पूछे दिन तेरे पीछे मैं कैसे तू ही ना हमसे जो बोले इश्क भीगे दिन है रूठे इश्क़े दी रावां तक दे चैन मैं खो दिया फिर तेनू दिल तो तड़के वापस ना खो गया फासलों से कम ना होती दिल लगी जो होती सच्ची कर निभा हम क्यों ना पाए कहीं वहीं पे बोले बिन कैसे ये बोले बिन तेरे पीछे मैं कैसे तू ही ना हमसे जो बोले इश्क भीगे दिन
Oh, Christ. What is this? Damn.
Boy 50. Yeah, I don't know nothing. How did you dirty? You did me disgusting. Said I was sorry, I couldn't be trusted. You calling me
Voucher. Hazur. There is always disturbance. Gundruk. Aha. So let's start again. We were at Carl Pearson's measure of skewness. So 3 mean minus median, 3 times mean minus median by standard deviation. Mean minus mode by standard deviation, as k is Carl Pearson's skewness coefficient, mean, median, standard deviation of data set. Skewness is equals to 0. The distribution is symmetric, means the mean, median, and mode are equal. Distribution is positively skewed, right skewed, with the tail on the right side longer than the left. Okay. When skewness is greater than 0, when less than 0, it's negatively skewed, left side longer than right. Okay. Calculate Pearson's skewness coefficient of a data set of exam scores. This, right? First, we'll calculate mean, which is 95.3, and calculation of median. Since there are 10 data points, the median is average of 5th and 6th values when stored in ascending order. 5th and 6th, and 96, 98, it's 97. Calculation of standard deviation, and we will calculate standard deviation, summation of xi minus mu square by n, root under, I guess. Yeah, root under. This is variance, and this is standard deviation. Standard deviation is 5, around 5. Calculation of mode. It is clear from the dataset that 100 is the most frequently occurring value in the data. Hence, mode of given data is 100. Right? Substitute the value in formula with respect to mean and median. It's 3 times x minus median, which is minus 0.2, and with respect to mean and mode 0.94. Since the skewness coefficient is negative, which shows a slightly negative skewness in distribution of exam scores, this means that the tail of the distribution is slightly longer on the left side, and most of the scores are concentrated on the right side of the mean. Okay, so it's negatively skewed because it's less than 0. Either you can do this or this, right? The Pauli's measure. Pauli's skewness coefficient is another method for calculating skewness based on quartiles. Unlike Carl Pearson's measure, it does not rely on the mean or standard deviation, which makes it useful for data that might not follow a normal distribution. It's calculated using the first quartile Q1, the second quartile Q2 or median, and the third quartile Q3. Q3 plus Q1 minus 2Q2 by Q3 minus Q1 is the formula of Bowley's measure. And first quartile is 25th percentile, 50th percentile or median, and 75th percentile. So if the value is equal to 0, the distribution is perfectly symmetric, no skewness. Less than 0, then it is negatively skewed. Greater than 0, it's positively right skewed. Okay. Calculation of representing age of a group of people in a sample. Is the middle value is 35, that is median, and calculate the first quartile. First quartile is 26, 24 plus 28 divided by 2, and to find Q1, let's consider the value left of the median. Okay. So 24 plus 28 divided by 2 is 26. Calculate third quartile. Right of the median is 40, 40 and 50. 42 plus 45, which is 43.5. Substituting the values in formula, It's minus 0.02, which is less than 0, which shows negatively skewed distribution, means the tail is longer on the left side, but it's little 0.02 is little bit. Kelly's measure. Kelly's skewness measure calculates skewness by comparing certain percentile in the data, which typically the 10th, 50th, and 90th percentile. This measure is used when dealing with data sets that are not normally distributed, or when other skewness measure may not be as effective. So it's P90 plus P10 minus 2 P50 by P90 minus P10. It's like Q3 plus Q1 minus Q2 by Q3 minus Q1. It's like 75th percentile, but now it's 90 and 10 and 50. Okay, median. So negatively skewed means the left tail is longer or heavier. Symmetric, positive skewed. Kelly's coefficient is calculated like this. Find percentile, we need to rank the data in ascending order to find the value below which percent of the data falls in this data set in correspond to value of position 1, since then 1, so percentile is 5. Median, this is average of 5 and 6 is 11, and 90th percentile is 18. 90% of data and point is 9, so 9th percentile is 18. And using the formula P90 plus P10 minus 2 into P50 by P90 minus P10 gives 2. This shows slightly positive skewed as longer tail on the right side. Interpretation of skew. Negative skewness. If the skewness is negative, it shows that the distribution is skewed to the left. In a left skewed distribution, this. If the skewness is negative, it shows that the distribution is skewed to the left. In a left skewed distribution, the tail on the left side, the smaller values, is longer and contains outliers. The majority of data points are concentrated on the right side. The mean is less than the median. Okay. 1 hour left around. Interpreting skewness involved understanding both the direction left or right and the magnitude degree of skewness of the data distribution. I'll be back. Okay. Today's day is like this. So it's the last day of 2025, so I'm getting lot of distractions. What should I say? Mm, interruption. Yeah, interruption. Let's say direction and magnitude. Okay, direction of skewness. Negative skewness, left skewed. If the skewness is uh, if the skewness is negative, it shows that the distribution is skewed to the left in a left skewed distribution. The tail on the left side, the smaller values, is longer and contains outliers. The majority of data points are concentrated on the right side. The mean is less than the median. Positive skewness, right skewed. A positive skewness shows that the distribution is skewed to the right in a right skewed distribution. The tail on the right side, the larger value, is longer and may contain outlier. Most data points are concentrated on the left side. The mean is greater than the median. There is skewness, symmetric or skewness value close to zero suggests a symmetric distribution where the data is evenly distributed on both sides of the mean. This means there is no skewness. Magnitude of skewness. The magnitude of skewness gives us information about how extreme the skewness is. Skewness close to zero between minus 0.5 and 0.5. The distribution is approximately symmetric. Skewness below minus 1. Strong left skewness, negative skew with a long tail on the left side. And skewness of 1. Strong right skewness with a long tail on the right side. Their skewness symmetric or skewness value close to zero, so symmetric distribution where the data is evenly distributed on both sides of the mean. This means there is no skewness. Okay. If there is an outlier, we have a danger. Not so much of a danger, but outlier is a danger and we have to take it out. Magnitude of skewness. The magnitude of skewness gives us information about how extreme the skewness is. Yes, and handling skewness in data. When working with skewed data, it's important to understand how to handle skewness effectively. Skewed data can impact the accuracy of statistical analysis and predictions. There are various methods to handle skewness depending on the nature of data and the analysis we want to perform. Let's see how we can handle skewness. Data transformation, log transformation. Yeah, using log, you can transform the data if it is left skewed or right skewed to normal bale. Okay. Uh, okay, for right skewed data. Sorry. I'm so naive. Data transformation. It is useful for right skewed data, compressing high values to create a more symmetric distribution. Square root, cube root. It helps reduce positive skew, especially for count data. Box count transformation, a flexible method for handling both positive and negative. Skew, box Cox transformation, not count. Square root, cube root. Log transformation is something I know. And removing outlier. Outlier can cause skewness, so removing them may improve symmetry. Z score, it identify and remove data points with Z score beyond plus minus 3. IQR method, interquartile range, it removes data point beyond 1.5 times the interquartile range. Uh, Non-parametric test, when transformations aren't effective, consider non-parametric tests like Mann-Whitney test, U-test, or Kruskal-Wallis test, which do not assume normal distribution and focus on medians rather than means. Okay, and these are something I learned in my uni. I learned in SAT 6 too, and this will be helpful. Yeah, yeah. Mm. Machine learning models. Some models handle skewed data better. Tree-based models, decision trees, and random forests are less sensitive to skewness. Generalized linear models (GLM) use appropriate link functions to model skewed data efficiently. Okay, difference between dispersion and skewness. While dispersion and skewness may seem similar, but they measure different aspects of data distribution. Dispersion refers to the extent to which data points are spread out from the central value, mean or median. It gives us an understanding of how varied the data is. Now let's see a tabular difference of for better understanding dispersion and skewness. Measures the spread of data around the central value, mean median. Measures the shape of the distribution and direction left or right. Variance, standard deviation, range, interquartile range, IQR. Fusion coefficient of skewness, movement, skewness, Q plot. Plots dispersion affects the mean interpretation but is not directly related. Skewness shows the relationship between the mean and median. High dispersion means data points are spread out widely. Positive skew right tail longer, left tail longer. Zero skew symmetric. Helps to understand the variability of data. Helps in identify the shape and asymmetry of data. Test scores spread, stock price variability, age, income distribution, right skewed, exam scored, left right skewed. By mastering concept of skewness and understanding its measurement, we can easily assess the data distributions, make informed decision, and apply the right techniques to our analysis. Done for date. The central limit theorem says that if we take many random samples from any population and calculate their averages, those averages will form a bell-shaped normal curve, even if the original data is not normally distributed, as long as the sample size is large enough. This helps us make predictions about the whole population using just sample data. Oh, good theory, good theory. Look. The central limit theorem says that if we take many random samples from any population and calculate that their averages, those averages will form a bell-shaped normal curve. Even if the original data is not normally distributed, as long as the sample size is large enough, this helps us make predictions about the whole population using just sample data. Okay, normal distribution. By calculating sample means, these averages will tend to form a normal distribution. This normality holds true as long as the sample size is sufficiently large, typically n is greater than or equal to 30, providing the foundation for making inferences about populations even when we don't have access to all the data. So, if n is greater than or equal to 30, the sample size is sufficiently large. Central limit theorem formula. You have a population where the data flows follows some random variable x, and this population has mean mu, the average of the population, standard deviation sigma. Let's say we take a sample of size n from this population and calculate its mean, uh, x mean. Then this z score is given below. Central limit theorem, z is equals to z mean minus mu by sigma by root n. This is the z score formula. Sample mean, population mean is equals to mu. Average of population. Sample standard deviation is equals to standard deviation by root n. Standard deviation by root n. As the sample size increases, the distribution of sample means becomes more concentrated around mu and resembles a normal distribution. As the sample size increases, the distribution of the sample mean becomes more concentrated around mu and resembles a normal distribution. Key assumption for central limit theorem. For the central limit theorem to work properly, a few conditions may be met. Random sampling, independence, large enough sample size, finite variance. Random sampling. The sample must be chosen randomly to fairly present the whole population. Each data point should be independent. One should not influence another. A sample size of at least 30 is usually enough for the sample mean to follow a normal distribution. Mm. The population should have a defined average, and variation, extreme or limited values, can make CLT unreliable. Okay, by ensuring these assumptions we are made, the theorem can be used to draw conclusions about the population. While working with CLT, we often need to work with skewed data. To learn more about skewed data, refer to skewness. We that we did that here. We did that here. Let's go to that anyway. Uh, oh, la la la. This much. अरे कहाँ गुंडा बनेगा तू? How? Finite mean variance, large enough sample size. Study usually enough for the sample mean to follow a normal distribution. Should be independent. One should not influence another. How CLT works in data science? You are data analysts at a tech company. Users around the world have different web page load times, usually being biased based on network speed and location. You need to estimate the mean load time, but it is impractical to verify every user. Let's solve this problem step by step. Problem identification. Instead of analyzing all users, you take a small sample, 50 users, to estimate the average load time. But since the data isn't normally distributed, can you trust this average? This is where the central limit theorem comes into play. Data sampling process. To use central limit theorem, take 50 random users and calculate their mean load time. Do it 1,000 times to obtain 1,000 sample means. Okay. Uh, when you graph these means, the outcome is approximately normal distribution, even though the original data is skewed. How to implement the CLT? Now that we understand the scenario, let's walk through the steps of how to implement CLT in using Python. Before its implementation, we should have some basic knowledge about NumPy and Matplotlib. We will generate fake web load times using an exponential distribution to represent skewed data. Take many random samples and plot their means to observe how they form a normal distribution. So we'll import NumPy as np and import matplotlib pie plot as PLT. np-random.seed population is equals to np.random.exponential. Okay, scale 2.0, size is this, and that's our population, which came from random. Okay, uh, which is generated randomly. Sample size is 50, number of samples 1000 times. Sample means don't know, that's empty list. Take samples and compute means. For dash in range of norm samples, sample is equals to random choice population size sample size, which is 50, and from population 50 seconds. Sample means append np dot mean sample, taken the mean, updated the value is, and plot the sample means. Histogram, sky blue color, black is beans 40. Sampling distribution of web page, load time means, and title is that sampling distribution load time, x label, y label, and grid is true. So grid is true. Grid came like this, and it's around this, and it became a normal. Okay. Although the original load time data is skewed, the histogram of sample mean shows a normal curve. This confirms the central limit theorem. Even non-normal data can produce a normal sampling distribution when you take enough samples. Okay, normal will be when you take enough samples. Practical applications of central limit theorem. The central limit theorem (CLT) is widely used in machine learning and data analysis. Model evaluation and confidence intervals. CLT helps build confidence intervals around model predictions, showing how reliable they are. Uh, More data leads to tighter intervals and more trust in results. A/B testing. A/B testing. I'm sleepy. A/B testing is used in product development. CLT ensures that average outcomes from repeated experiments become normally distributed even with skewed data. Error and uncertainty estimation. CLT allows us to estimate prediction errors and standard errors, helping assess model uncertainty on new data. Bootstrapping. By resampling data, CLT supports reliable estimation of metrics like MSE and confidence intervals for model parameters. Feature importance. CLT helps check if feature rankings remain stable across samples, ensuring the most consistent and reliable features are chosen. Limitations of central limit theorem. The limitation limit central limit theorem (CLT) is a useful concept in statistics, but it comes with some limitations that are important to understand. Let's understand them one by one. Sample size. CLT is efficient for large samples. CLT will not work with very small samples, particularly with data that is skewed, and mean will not follow normal distribution and may result in erroneous conclusions. Population shift. While CLT can apply to any population, if the data is very uneven or has extreme values, you will need a much larger sample for the average to become normal. Okay. Independent data. The data points in your sample must be independent. This isn't true for things like time series data, where one value depends on the previous one, which can affect the results. Random sampling. The sample needs to be selected randomly. If it is biased, example only sample from a specific group, then it won't accurately represent the entire population, and CLT won't function as intended. Finite variance. The population should have a well-defined limited range in values. If variation is infinite or too large, the NCRT does not apply. Hypothesis testing. Hypothesis testing compares two opposite ideas about a group of people or things and uses data from a small part of that group or sample to decide which idea is more likely true. We collect and study sample data to check if the claim is correct. Use of skewness. Oh, oh, just use. Good, 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 good. Way of the dead. Way. Hmm. Yeah, null hypothesis, alternative hypothesis. And for example, if a company says its website gets 50 visitors each day on average, we use hypothesis testing to look at past visitor data and see if this claim is true or if the actual number is different. Defining hypothesis, null hypothesis, as no. The starting assumption, for example, the average visits are 50, right? Alternative hypothesis, the opposite, saying there's a difference. For example, the average visits are not 50. Key terms of hypothesis testing. To understand hypothesis testing, firstly, we need to understand the key terms which are given below. Alpha, how significant level, how sure you want to be saying the claim is false. Okay, how sure you want to be to claim that as not is false. Usually we choose 0.05, 5%, that's normal. And p-value, the chance of seeing the data if the null hypothesis is true. If this is less than alpha, we say the claim is probably false. If it's greater than, it's true. Right. Yeah. Yeah, we accept null hypothesis when p-value is greater than alpha. Test statistic, a number that helps us decide if data supports or rejects the claim. Okay. Uh, Critical value, the cutoff point to compare with the test statistic. Degree of freedom, a number that depends on the data size and helps find the critical value. Types of hypothesis testing. It involves basically two types of testing: one-tailed and two-tailed, right? One-tailed, a by 2, where we do not reject in these but we reject in these, right? If it goes from this, then we'll reject at this is left-tailed, and this is right-tailed, so we do not reject here but we'll reject from here. And two-tailed are equal or not equal. Left-tailed are greater than or equal to or less than, and right-tailed are less than or equal to or greater than, right? One-tailed test used when we expect a change is only one direction, either up or down, but not both. For example, if testing whether a new algorithm improves accuracy, we only check if accuracy increases. So we are there are two types of one-tailed tests: left-tailed and right-tailed. Check if the value is less than expected. Example, as not mu is greater than or equal to 50, or mu is less than 50. Right-tailed test checks if the value is greater than expected, mu is less than 50, or mu is greater than 50. Okay. For this one-tailed test, it's exactly opposite of this. Right. If mu is less than 50, then it will be left-tailed. And two-tailed test used when we want to see if there is a difference in either direction, higher or lower. For example, testing if a marketing strategy affects sales, whether it goes up or down. Okay. And example is as not mu is equals to 50, and h1 mu is not equal to 50. To go deeper into differences of port types, test refer to link. Uh, Here we can learn one tail and two tail test. It will be there. I'll look at it. I guess it's not very deep, but we learned it in uni. So in hypothesis testing, type 1 and type 2 errors are two possible errors that can happen when we are finding conclusions. We read about it earlier to publish in this. These errors are associated with decisions we made regarding the null hypothesis and alternative hypothesis. When we reject the null hypothesis, although that hypothesis was true, type 1 error is denoted as alpha. When we accept the null hypothesis but it is false, type 2 error is denoted by beta, and beta is more killer than alpha. Okay, it is more of a error. Correct decisions, type 2 error, false negative. So uh, null hypothesis is true, null hypothesis is false, type 2 error, false negative. Okay, we accept but the null hypothesis is false. We reject and or we reject the null hypothesis and the null hypothesis is false. Then correct decision, we reject null hypothesis but null hypothesis is true. It's type 1 error. False positive. False positive, false negative. False positive is rejecting alternative hypothesis when null hypothesis is true. Okay. No. Rejecting null hypothesis when null hypothesis is true. Then it is type 1 error. And when we accept the null hypothesis, when null hypothesis is false, it's type 2 error. That is type 2 error is false negative, type 1 error is false positive. False positive, false negative, false positive, false negative. Okay. It's more deadly, so it's negative. Let's remember it like that. How does hypothesis testing work? Working of hypothesis testing involves various steps. Define null and alternative hypothesis, choose significance level, to collect and analyze the data, calculate the test statistics, do not reject as not, conclude as not may be true, reject as not, conclude as not is true. As A is true, alternative is true. Okay. Step 1. Define hypothesis. Assume no effects or differences. Assume there is effect or differences. Okay. Test if a new algorithm improves user agreement. So, if there is effect, then we'll test alternative hypothesis greater. Improves means greater, right? In this, we assume that our data is normally distributed. Okay. So, significance level. We select a significance level usually 0.05. This is maximum chance we accept of wrongly rejecting the null hypothesis. Type 1 error. It also sets the confidence needed for to accept results. Okay. Collect and analyze data. Now we gather data. This could come from user observation or an experiment. Once collected, we analyze the data using appropriate statistical methods to calculate the statistical test. Okay, we're back. We're back. So we were at step three. I was reading step three, muted, and then to step four. Okay, fine. 26 minutes. Mm, let's read again. The test set 6 measures how the sample data deviates from what we did expect if the null hypotheses were true. Different tests use different statistics. Z-test uses used when population variance is known and sample size is large. T-test used when sample size is small or population variance unknown. Chi-square test used for categorical data to compare observed versus expected counts. Step 5. Make a decision. We compare the test statistic to a critical value from a statistical table or use the p-value. Okay. We compare the test statistics to a critical value from a statistical table or use p-value. Using critical value, if test statistic is greater than critical value, then we reject null. If statistics is less than critical value, we fail to reject as not. Null hypothesis means there is no change. Using p-value, if p-value is less than alpha, reject as not. If p-value is greater than alpha, fail to reject as. Okay, it's opposite. P-value and critical value are opposite. Interpret the results. If the p-value is 0.03 and alpha is 0.05, we reject. Okay. Interpret the results. Based on the decision, we conclude whether there is enough evidence to support the alternative hypothesis or if we should keep the null hypothesis. A pharmaceutical company tests a new drug to see if it lowers blood pressure in patients. Data before treatment 120, 122, this, after treatment, this. Define the hypothesis. The new drug has no effect on blood pressure. The new drug has an effect on blood pressure. Okay. Define significance level. Usually 0.05 meaning less than 5% chance. Results are by random chance. Huh? It's alpha 0.05. Okay. Compute the test statistic using paired t-test. Analyze the data to obtain a test statistic and a p-value. The test statistic is calculated based on differences between blood pressure measurements before and after treatment. T is equals to m slash s slash root n, where mean of the differences x after and x before. X after minus x before, standard deviation of the difference di, x after I and x before I, sample size return n. Okay, it's x after minus x before by as standard deviation x after I minus before I pi root under n. Means, yeah, like that. That is, then m, s, n are that, and we calculate test set 6 minus 9 based on the formula for paired t-test. I find the p-value with degree of freedom n 9. Find the p-value with degree of freedom 9. P-value is very small, and result, since p-value is this is less than the significance level 0.005, the researchers reject the null hypothesis. There is statistically significant evidence that the average blood pressure before and after treatment with the new drug is different. Python implementation of case A. Now we will implement this using paired t-test with the help of SciPy stats. SciPy is a mathematical library in Python that is mostly used for mathematical equations and computations. We use NumPy library for storing the data in arrays. NumPy as NP, SciPy as stats. Both are the arrays that were given before and after. Alpha is 0.05. Test statistic, p-value, and test stats dot t test rel a and b. M is np mean, a minus b mean of after and before, difference of mean of after and before, x minus x. Okay, and s is np dot standard deviation. Okay, after and before. Okay, and n is equals to length of b, that is array, length of array, and t manual is equals to m slash s slash nb square root of n given length decision. Reject if p-value is less than alpha, else filled, and that is the answer. Significant difference. The test statistic of about minus 9 and a very small p-value provide strong evidence to reject the null hypothesis at 0.05 level. This means the new drug significantly lowers blood pressure. The negative t statistic shows the average blood pressure after treatment is lower than before. Limitations of hypothesis testing. Although hypothesis testing is a useful technique, but it has some limitations as well. Limited scope. Hypothesis testing focuses on specific questions or assumptions and not capture the complexity of the problem being studied. Data quality dependence. The accuracy of the results depends on the quality of the data. Poor quality or inaccurate data can lead to incorrect conclusions, missed patterns. By focusing on only on testing specific hypotheses, important patterns or relationships in the data might be missed. Context limitations in it doesn't always consider the bigger picture, which can oversimplify results and lead to incomplete insights. Need for additional methods. To get a better understanding of the data, hypothesis testing should be combined with other analytical methods such as data visualization or machine learning techniques, which we study later in upcoming articles. Dun, 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 dun. Use of skewness, central limit theorem, and hypothesis testing. Dot dot dot. This no comments. This isn't most theoretical. No discussion. Wow. So, in data science, we often work with samples instead of entire populations, right? We can't calculate the entire population. Well, it is known universally. The central limit theorem (CLT) helps us assume normality in sample means, while hypothesis testing helps us make decisions based on those samples. These concepts are essential for tasks like A/B testing, model evaluation, and user behavior analysis. Skewness in data set. Skewness tells us whether the data is symmetric or tilted to one side. Understanding skewness is important because before applying statistical methods that assume normality. Income distribution. Suppose a company's employee salary are this. Most salaries are around 25 to 36, but one outlier, 100K, pulls the average to the right. This positively skewed distribution, the mean will be higher than the median due to the high income outlier. Central limit theorem (CLT) in data science. The central limit theorem says that if we take many large samples and find their averages, those averages form a normal distribution even if the original data is skewed. This allows data scientists to use normal distribution formulas to calculate confidence intervals and error margins even when the raw data is not normal. Okay. Example, estimating average daily orders. A delivery company wants to estimate the average daily orders without checking the full month's data. Okay, population mean is 360. Sample mean and average sample mean is this. This shows how the central limit theorem helps small samples give a reliable estimate of the overall mean. Use cases. Estimate delivery time from few days, analyze average spending from user samples, approximate server time without full logs. Hypothesis testing in data science. Hypothesis testing. Hypothesis testing in data science. Hypothesis testing checks if a sample result is statistically different from a known or expected value. It helps in deciding whether to reject the null hypothesis based on threshold called the significance level, commonly 0.05, as the complaint rate decreased. Example: a company claims its new packaging reduced complaints. Earlier, 10% of cost orders had complaints. In a recent sample of 1,000 orders, only 70 complaints were reported. Complaint rate 10%, complaint rate less than 10%. Okay, null hypothesis is complaint rate is normal, is 10%, and complaint rate is reduced. Okay, sample rate 0.07. Its sample rate is 0.07 sample rate, and Z test is 3 minus 3.16. Critical is minus 1.645. Since less than, we reject. As known, there is strong evidence the complaint rate has dropped. Applications. Since test if a website change improves clicks compared to ML models. check if discounts increase sales, evaluate impact or process update. But it doesn't look at bigger picture. Okay, quiz. Let's do quiz. There are 8 quiz and we are around at 2 hours clock. So why does the central limit theorem work even if the original population distribution is not normal? Okay, because the sample mean will always be identical to the population mean. Hmm. As sample size increases, the distribution of sample means become approximately normal. Hmm. Because the population data always follows a bell curve. Hmm. Random sampling removes all skewness from the data. Ooh, interesting. This one is hard. This one is hard. Okay. This one is hard. It says go to articles. It's central limit theorem work even if the original population distribution is not normal, right? It works even if the original sample is not normal because the sample means will always be identical to the population mean. Uh, Shit, I changed the audio input capture, bro. Damn. Uh, there should be less volume right now, I guess. Input capture, I have to get out to. Mm, yeah. 1, 2, 3. It should be okay now. If I even touch the input rate, it doesn't work. These two I am doubtful. This one I am also doubtful that I. We'll come back. This is not. Mm. Shit. Fail to reject, right? If p-value is less than alpha, then we will reject the null hypothesis. If greater, then we will accept the null hypothesis, right? Yes. This is also these two. Hmm. Now tomorrow we'll learn test. Hmm. Let's see. For today, I'll be going there. And this much for today. We rate skewness, central limit theorem, and hypothesis system. If tomorrow it goes fast, then we can learn these two: calculus, manual test, Bayesian statistics. Oh, wait. Basics of NumPy arrays, Python pandas, and in all values duplications. Okay, these are all for exploratory analysis, visualization, and machine learning, logistic regression, classification, project. Okay. What is this? Let's see.
Hi and welcome back to the video, guys. Yeah, so in this video we're going to discuss about a small project in logistic regression, that is hard disease prediction. Yeah, before going into the regression, let us see what we have here. So in ML we have two of the major components, that is classification as well as the regression. So majorly in this video we're going to discuss about one of the type in regression, that is logistic regression, and other type we have, it is linear regression. All right, but in this video we're going to discuss about this thing. All right, yeah. So basically, what is logistic regression? Consider we have two components called independent variables and dependent variables. All right, if you take the example of a car price prediction, you have many, what we say, attributes or the variables inside that. You can consider the model name or price or the engine type and whatever it is. So here, as we are trying to predict the price value, your price will be the dependent variable. So whatever the input you are giving, it will be the independent. For example, you are giving your machine learning model, you are giving your car model preferences to your logistic regression, and it is giving you the output as your price. All right. So what's happening inside is, inside your machine learning model, you have your dependent variable. So ultimate dependent variable is price, right? So inside your machine learning model, you have price. This price will be waiting for one independent variable. So using that independent variable, this dependent variable will be calculating some statistical models or statistical calculations and give an output as a predicted price. So this is how it works. But yeah, see, this is how regression works. But logistic regression works like, logistic regression will be using one of the function called sigmoid function. All right. So whatever the independent variable you have, independent variable, it will be so this sigmoid function will be taking this independent variable and it will be giving the probability value. All right. And this probability will be lying between 1 and 0, 0 and 1. All right. For example, you have two classes. Let us consider. You have class 0 and class 1. Okay. So using the independent variable and sigmoid function, you'll get a probability value of 0 and 1, right? For example, if you got a probability value which is greater than 0.5, so your value will be going to your class 1. Or else, if you got a value which is less than 0.5, your probability value will be going to class 0. So this is how logistic regression will be classifying its output value. But yeah, as I said, in machine learning model, we have both the things called classification and regression. But here the functionality of the logistic regression is similar as the classification, right? But see, we have a difference here. Whenever you're taking an input from the user as an independent variable, you'll be getting one term called threshold value. Threshold. So using the threshold value, input variable and sigmoid function will be getting a probability value. All right. The logistic regression is just classifying this probability value, but it's not the same thing with classification. What classification does is, if we have a labels like name, age, what we say, school or marks, something like that, based on the data we have, this data will be segregating between these labels. But when it comes to the logistic regression part, it's not like that. We're calculating the end probability. Using the end probability, we're classifying between the both of the classes. So all this theory, we call it as a categorical data set. All right. So we are just dealing with segregating the categorical data here. So that's the reason we call it as categorical data set. We are ultimately creating a data set which will be dealing with the categories. So yeah, this is about the logistic regression. So coming to the first step, we need to import the necessary libraries here. So these are some of the important libraries which we are going to deal in this project. All right. Yeah. First, coming to pandas. So as you know, pandas will be dealing with the big data sets. It will be helping in manipulating the data set or deleting or adding some of the columns or rows in that. And coming to Pylab, Pylab will be helping to import the functions of NumPy and MATLAB. Okay. Yeah. And coming to NumPy, will be helping with dealing with numbers, arrays, and like that. Okay. And this will be helping in optimizing the algorithm, or it will be helping in improving the algorithms which you are choosing. And this library will be helping in improvising or increasing the performance of the statistical model. And yeah, we call our logistic regression as a statistical model because this will be taking the values of probability as a binary number, and using those statistical numbers, it will be building the model. So that's the reason we are calling it a statistical model. And yeah, where did we stop? Yeah, sklearn. And this sklearn will be helping in, what do you say, providing some of the tools which will be helping in increasing the speed or training the testing the data sets like that. It will be providing some of the tools to us. And coming to math.lib, as you know, it will be helping us in visualizing the data like confusion matrix or some of the bar graphs or pie charts like that. It will be helping in visualizing our data set. And Seaborn, it will be using to understand our data. Whatever the data set we are giving to the model, it will be helping us to understand the data set. So these are some of the useful libraries which we are going to use in this project. Let's go to the further slide. So whatever the projects you are taking at first, we need to prepare our data, like importing the data set, manipulating it by removing or adding some of the columns like that. See, in most of the projects, we'll be getting a data set in which all of the columns or all of the rows are not necessary to us. So we are trying to remove some of the columns or rows because if we have unnecessary or irrelevant data points inside it, the load for the model will be increasing and accuracy might decrease. So that's the reason we will try to manipulate some of the data columns or rows like that. At first, I'm initiating a variable which will be taking the CSV file as a data set.
Okay, we'll be looking at it later. I know. Load, and I'll see you. Okay, we'll be looking at that eventually. So I'll try if I can do the 10 and 11th January 1. And for today's session, this much. Bye bye 2025. It's 31st December, and we'll see you at 2026. Bye.